last speaker is Gwinn. We scheduled from last week due to an airline issue. Apparently not always competent. So we have this slightly less common time slot. Nevertheless, we're happy to have Gwinn visiting us from Santa Barbara. Carl is a seminar speaker, apparently first time speaking here in Toronto, much to our honor. It's one of the invitations that was kind of out of the cold. We've never actually met before. And I've had multiple recommendations that he would be a great person to get to talk about a lot of interesting ideas and developments that Carl has made over many years. And we're very happy that it's actually happening. So,
well, thanks very much, Yuli. It's a great pleasure to be here. I've come across Yuli's papers for many years, and it's kind of amazing that we haven't met. It's a great pleasure to be here and to be talking with him and his colleagues. My main topic today, I will jump right in, is to talk about Earth space interferometry, and in particular about the Radioastron mission. And we're also fortunate to have here today Wayne Cannon, who has been working on the Radioastron mission, as he told me, for almost 30 years. And it was a long-running effort that required huge dedication on the part of the people who built and hurled it into space. These are some of my principal collaborators. Mikhail Popov, who's at the Aerospace Center in Moscow. Michael Johnson, my former grad student, he's now at Center for Astrophysics. And Yuri Kovalev, also at the ASC in Moscow. And Nikolai Kardashev is I suppose the PI of the spacecraft, the prime mover, as well as well known to you for work on recombination lines and extraterrestrial intelligence and so forth. And Volodya Shishov is a rather distinguished Russian worker on scattering and scintillation. And so we have many other collaborators, including Norbert Bartel, who is at York. So here's the outline of my talk. First, I'll tell you a little bit about the Radioastron spacecraft. And I'll tell you about the results briefly for active galactic nuclei, which have been quite interesting. The impulse response function for scattering in the interstellar medium, and specifically the Crab Pulsar. So this part is about pulsars. And structure in the image of heavily scattered pulsars, notably Vela and O329 plus 54, which that is the brightest pulsar visible in the northern hemisphere. And then this substructure in the scattered image of Sag star. So this Radioastron is a 10-meter radioastronomical antenna. It's in a 9-day elliptical orbit with a perigee not much above an Earth radius and an apogee at about the distance of the moon. It has 4 wavelength bands of a meter and 18 centimeters. Those are the ones I'm most interested in, although it does have 1.3 centimeters. And it has an onboard hydrogen maser. In fact, it has 2, one of which is working. So it's quite a sophisticated system. OK, so this is the actual antenna. There's Mikhail Popov showing how big it is. This is in a clean room in Moscow on the ground. So the spacecraft bus is attached down here and contains power supplies, solar panels, and ground link. And the receivers are up there. This is the launch in Baikonur, an event that many of the people who were working on this had been working for 25 years or more to get this into orbit. And it was quite a pleasure when it lifted off into space. So these are some results just for active galactic nuclei. I think these were the reason the thing was put in orbit. And Yuri Kovalev is the leader of this project. These are results for 18-centimeter wavelength. And what you see is that there are detections. There are quite a few detections on just a few Earth diameters. So resolutions of order a few milliarc seconds. But there are resolutions out to 28 Earth diameters, about the distance to the moon. So some of these sources have remarkably compact structure in their central engines. This is the brightness temperature. As you can see, it exceeds, in a few cases, or it approaches and exceeds 10 to the 14th Kelvin. 10 to the 12th Kelvin is in practice the limit for a incoherent synchrotron emission because of the Self-Compton cascade. So these sources, and then something like 10 to the 10 Kelvin is probably a more reasonable value for the brightness temperature of a synchrotron emitting plasma. That's the limiting brightness temperature for one that's in equipartition between magnetic fields and kinetic energy. So these sources probably are shining by some either a coherent emission process such as a cyclotron maser near the black hole, or possibly proton synchrotron radiation, something like that. So I can say a few more things about AGN, but I'd rather shift to pulsars, which have been my focus for the project. So the first object I'll discuss, and the first object, in fact, that the spacecraft observed was the Crab Pulsar. And the reason for this is that the Crab pulses the Crab occasionally emits pulses that have something like 10 to the 5th times the average flux of the pulse. So in fact, most of the flux density of the Crab Pulsar in the radio comes out in the form of giant pulses, somewhat like the income distribution in the US, where most of the money belongs to a very small fraction of people, or wealth distribution, I suppose. So, and one of the advantages is, but let me describe a little bit what happens to these pulses when they're scattered. Even if the pulsar were to emit a delta function spike of electric field, that spike would propagate along many paths through the interstellar medium and arrive over a variety of times and with a different number of phases. So in fact, this can be described as a convolution of the electric field of the source with an impulse response function, a Green's function for scattering. That Green's function actually varies with position of the telescope, so that if you move away, these different lines of sight that those spikes reach you have different lengths. And so these spikes, these responses have different arrival times and different phases. And the scale for that variation is typically a few Earth radii. So there's a lateral scale in the plane of the observer. So this is one giant pulse. This is one of the first observed, which was at Radio Astron. This is the pulse observed at Westerbork. You can see it has a very complicated internal structure with sort of a fast rise and slow fall. Here it is. I suppose these weren't, the stations aren't listed here. This is actually the pulse observed at Radio Astron. And you can see, although the noise level is high, noise level, this was improved later. But you can detect a pulse here. Let's see.
These are different pulses?
Sorry, these are different stations. So this is the pulse observed at Westerbork in Holland. Here it is observed at Jodrell Bank. Urumqi, which is in western China. This is Effelsberg, and then Urumqi, and then Radio Astron. So it's sort of a sequence. With Westerbork probably the most sensitive, and Radio Astron definitely the smallest. But what I'd like to draw your attention to is that if you look at these three strongest peaks, they appear very similar at these three European stations, almost identical. If you go to Urumqi, there's definitely some variation from this. And at Radio Astron, the pulse is actually rather different. So the conclusion here is that this structure arises at least partly, if not entirely, from the impulse response function. It's consistent with the pulse generated at the pulsar being about a nanosecond in width, and this just reflects propagation physics, possibly, certainly in the interstellar medium, since we're seeing it change on this scale to 220,000 kilometers, and possibly also in the pulsar magnetosphere. This is a different pulse. Alexei Rudnitsky is the Russian graduate student who is working on this. So what we do is we take individual giant pulses, and we correlate them between ends of between two antennas, and then we try shifting them by any amount. And maximizing the correlation. So these are Russian stations. BD is Badari and SV is, I can't remember. But you can see that for short baselines, the correlation is quite good, and it's sharply peaked, although there's a little bit of low correlation surrounding that. So there's sort of a series of lags of the two pulses at which the correlation is good, but not as perfect as if they're perfectly aligned. On the other hand, once you go to this space baselines, this telescope at about 100,000 kilometers, what you see is that the correlation is present, but certainly not as sharply peaked. There's some evidence of a sharp peak in some cases, but generally you just get sort of a mush. So this is Alexei's summary of these. And what he did was he just took the peak of that correlation function and plotted as a function of baseline length in Earth diameters out from 0 to 10. And what he found was that the peak does indeed decrease with baseline length from about near 100%. Interestingly, not quite 100% even for very short baselines, out to something like 50%. So this is a very coarse model that is supposed to just kind of guide your eye through these points. And the idea here is that, well, the correlation is decreased to about 50% at this point. So that defines the lateral scale of this correlation function in the plane of the observer. And in fact, that scale is, this should say SIS, but this is also the baseline at which the correlation drops. So you're separating the antennas by enough to drop the correlation to 50%. So that's also defines the angular size of the scattering disk. So the scattering is about 0.3 milliarc seconds at this wavelength, 18 centimeters. You can also do the experiment at 92 centimeters, and you find that because the refractive index of plasma is like lambda squared, you find that the correlation, this length is correspondingly smaller at that longer wavelength. Okay, so just to summarize this, giant pulses were detected, several in single dish mode. Initially, this was used to synchronize the clock, although because of the problem with the decorrelation, the clocks couldn't be synchronized very accurately on the spacecraft using this. And if you compare the angular extent of that correlation function with the time lag, you can compute that the scattering takes place in the Crab Nebula and maybe even well inside it, and possibly some of it is inside the magnetosphere. There seems to be quite a bit of variability of the scattering from one pulse to the next. We don't have as many pulses as we'd like. But this provides you with a feeling for what the impulse response function is like. Okay, so now I'm going to talk about a slightly more complicated project and then a slightly simpler one. This has been my project along with Misha Popov. And the idea is to try and image pulsars is essentially the idea. Try and see what they look like if at very high angular resolution, including the phenomenon of scattering, see what that looks like. And I'll tell you the punchline. The scattered images contain very rich structure, and the statistics are nearly noise-like, but possibly not quite. So the idea here is that this impulse response function changes over this lateral scale of a few Earth radii. And as the Earth moves and carries these antennas across the observer plane, this impulse response function varies. If you want, you can Fourier transform the power. You can measure the power spectrum in frequency space. And it turns out that's the product of Fourier transforms of the impulse response function. So what we're looking here, in fact, is the same thing as we looked at with Crab. We're just looking at it in the conjugate frequency domain. And if we look at a short baseline, then these two functions are the same, and this has to be real and in fact positive. So this is what it looks like. This is the so-called dynamic spectrum. The horizontal component is frequency. So each line across here shows what the impulse response function is at a particular instant in time. And then it's the Fourier transform of that. And then as you move upward, that function changes. And the phase, however, the complex phase of that function is of course 0, since you're taking something, taking its square modulus, and Fourier transforming it. Okay, and and perhaps it's worth saying that obviously there are these random changes in the impulse response function. Well, the frequency of that change is about the time span of that impulse response function by the uncertainty principle. And then the time span of this change is about the time for the Earth to move through the lateral scale of the impulse response function. Okay, so here's some data, and this I didn't find the phase, but this just shows the amplitude on a baseline of 0 length. This is the autocorrelation of the Green Bank telescope with itself for, this is for the pulsar 0329 plus 54, the brightest pulsar in the northern sky. Okay, so let's think about putting one of these antennas on a spacecraft and moving one of these impulse response functions outside this lateral scale. And well, what we expect is that the phase will be completely random if these guys are completely uncorrelated. So we should see just the product of two similar but random functions. And the Fourier transforms of those should look something like this. Some random amplitude, this is a simulation, and some random phase that goes between 0 and 2 pi. And here's some data. This is the amplitude, and you can believe that this looks like that. This is from the Green Bank telescope to Radioastron, the Space Radio Telescope. And here's the phase. This is a little bit of a different plot. This just follows the phase of some of these maxima. Sorry, these maxima. It follows the phase up. And you can see that the phases remain, well, they vary with time, and in fact go through an inflection point here. We think that this time variation is due to the ionosphere, but also the phases of those different maxima are different. So these are phase differences amongst, I guess, this line, for example. This is, let's see, this is 315. And so that's this long stripe, and its phase varies like this. But its phase is different, say, from phase 90, which is that stripe. Okay. So there's this interesting old prediction of substructure in scattering disks. I could describe physically, I will describe physically where that comes from. But the basic idea is that, that this correlation that I mentioned should fall off roughly like a Gaussian. This is a log scale, possibly with a major axis and a minor axis, which have different sizes. But then out here, the prediction is you should nevertheless detect something, even though you expect these correlation functions to be completely uncorrelated. This is actually a little sort of eggs and apples plot. These curves are averages. So this a particular short observation, because of that randomness among the scintillations, will produce some variations around that average. But these are just the RMS about 0. So you'll see something, but that will trail off gradually. Okay, so in order to compare these complicated random plots with these data, what we did, in fact, was we Fourier transformed them. So what are these? In fact, what these are, they should look exactly like the correlation functions for the crab, the time series of the crab. So at 0 lag, you expect that those patterns are identical, and there should be a spike. As you translate them away, you should see, well, there's still some correlation, but it should gradually die away as those time series are translated by enough to that they don't overlap at all. So it should have the same characteristic shape, and so this dimension should be something like the characteristic frequency scale of the pattern, and this should be the characteristic time scale. So it's a two-dimensional FFT. So this is what a short baseline would look like, just as for the crab. Not zero, but short. And this is, in fact, what we see. This is a cut through the observed autocorrelation function for 0329 plus 54. And you see this kind of nice, pretty much Gaussian with a nice spike. Yeah, and it has these dimensions. This is roughly 1 over the scintillation timescale. And this narrow spike is just 1 over the total bandwidth, since you can't see structures smaller than that. On a long baseline, the central spike goes away because the phase is random. There's no and the peaks are still distributed over this scale. And so this is a color plot, not a 3D plot, of the correlation function for the Vela pulsar. And indeed, what you see is it's concentrated into this expected region. OK, so the traditional technique in radio astronomy is you don't expect all this randomness. You expect things to be quite uniform across the band. And so you expect there to be a single spike. In fact, what you expect to see is what we would see on a very short baseline. So the traditional fringe search technique is to find the biggest spike and record its amplitude and forget everything else because it's not important. So really, for us, it's not really a very good measure of how strong the source is or anything. But nevertheless, it's the tradition. But each of these other peaks, in fact, the central peak, it's a sum over the dynamic spectrum. A Fourier transform is just a sum with phase factors thrown in. But here it's a sum of elements with random phase and amplitudes. And those are multiplied by the Fourier phases. So it looks like a random walk is to a good approximation or some approximation. It's a starting point. So if you believe this, then the central limit theorem says that these should just be drawn from a Gaussian distribution. And where this one happened to be particularly lucky, and it has some neighbors who were particularly unlucky. And so this shows we took a very large set of data, and we Fourier transformed them, found the largest peak for each one, and drew a dot. And this shows how the amplitudes of those dots change as we increase the integration time and increase the bandwidth. And what you see is that up until integration times of about 15 seconds, the scintillation time, the amplitude remains pretty much constant. But once you're beyond 15 seconds, it goes like 1 over the integration time to the 1/2. So in other words, this should be a minus 1/2, sorry. So in other words, this says that indeed those fringe plots look like random walks. So I think maybe to summarize what's going on here is we're trying to study something that has very complicated random statistics with tools that were developed to study something that was completely deterministic. And so we don't know quite how to do that. We've been trying various things. One is to take a small window in this and say, well, these peaks should have statistics of a random walk. Let's see if they do. This is the result of one such experiment. So this is not the amplitude. It's the square of the amplitude of those peaks in that window. And here we have the number as a function of the size. And what you see is this follows a straight line. It's an exponential distribution of peak heights. And since that's amplitude squared, the distribution of peak amplitudes is Gaussian. or is consistent with Gaussian. So it says that this structure is completely consistent with being completely random. So yeah, so I guess we detect the thing. We get beyond the scale of the scintillation pattern. Our problem is we have to deal with a distribution of fringe amplitudes. The interference fringes have some distributions. And that distribution is approximately noise-like, and to about 10 to the 6 samples.
What do you mean if you say noise-like?
Well, that's a great question. I think the most I would say it would say that any visibility of the scattering disk would be drawn from a Gaussian distribution with some variance that is and that there's no correlation among elements.
In the 15 seconds, is that interpreted as the path length difference?
The 15 seconds is the time that it takes for the entire system to move by one SIS, but to move by one scale. Yeah, so thanks for the questions.
How do you distinguish, I mean, the statistical properties come from the scattering, but the scattering can take place either near the source or in the interstellar.
Yes.
How do you know
Well,
where it comes from?
for example, with the Crab Pulsar, where I said that the scattering could be partially magnetospheric, I think it's a matter of plausibility arguments. And for the Crab, one phenomenon is that these giant pulses show very different behavior between pulses, and sometimes you can get them quite close together. So you can argue that, well, and they even show up at different dispersion measures. And so you can make the argument, well, if these giant pulses are changing so dramatically in less than a scintillation time scale, then it must be intrinsic. And that is the argument I would like to make. We don't have enough data to make it as of yet. I suppose another interesting factoid is, I guess, or let's see, if the scattering should be coherent in the sense that every line of sight should carry a copy of that original delta function. And on the assumption that the scattering is random, if you have a lot of samples of it, you should see that the amplitude of electric field is drawn from a Gaussian distribution, since the electric field at any instant is the sum of a lot of different paths, that it's a random walk. Of course, unfortunately, our statistics are limited, but it seems that the electric field isn't drawn from a pure Gaussian distribution, so the scattering is not completely coherent, which is a lot easier to understand if it's in the magnetosphere. So that's, Alexei Rudnitsky has a lot on his plate. So I'd like to finish up by talking about a somewhat different project, which is substructure in the scattered image of Sag star. So this compact galactic radio source at the center of the galaxy it's coincident with a 4 million solar mass black hole, and it's heavily scattered at wavelengths longer than a millimeter. This is just a plot of the size of this source, major axis and minor axis, plotted with wavelength, and theta goes like lambda squared over a couple of orders of magnitude in wavelength, with some indication that it's curving upward here at wavelengths of a millimeter or less. So, of course, the Event Horizon Telescope hopes to go over here to about 1/10 of a millimeter, where scattering can be neglected. Well, there's one interesting thing about this plot is I'd like you to draw your attention to these two, to these 2 points. This is a report by Ken Kellerman from 1977 of VLBI observations of this source. And what he saw was that as a function of baseline length, the correlation dropped rather precipitously, but then remained flat. And now this domain is, of course, the Fourier transform of the image domain. So a large source will quickly decorrelate on a long baseline, whereas a compact source will have zero visibility. So this indicates a compact component that has a flux density of maybe 10% to 25% of the maximum. So this is somewhat like this compact structure in a scattered source that we saw. So this motivated us to observe the source with the Green Bank telescope to provide additional sensitivity, as well as the very long baseline array. And this is what we saw. So the blue points are VLBA to VLBA baselines that detected the source, and the red points are Green Bank to VLBA baselines that detected the source. And the green line is what you would predict for the visibility of the source, the correlation from that plot of size as a function of baseline length. So this is just a Gaussian distribution of flux density on the sky. And it should continue to go down like this. And out here it should be like 10 to the minus 9, 10 to the minus 12 Janskis. So what we're seeing is that nevertheless on these long baselines we're picking up some correlation of flux density. And if you take this Goodman and Narayan theory and assume that the source is point-like, which clearly it isn't, then these are the quantiles. The distribution of flux density should be Rayleigh distribution with a 50% line here. Of course, it appears to be a little less than that. Maybe it's worth pointing out that this is a lot less than what Kellerman saw, which was more like 10 or 25%. So this shows detections as a function of, this is the so-called UV plane. It's the Fourier, sorry about all the Fourier transforms. This is the Fourier transform of the image. So if you look at the sky, you see an ellipsoidal average source. Fourier transform that, and you see an ellipsoid that has a 1% level at these red dots. And then the VLBA baselines show, which are the black curves, show detections inside of that ellipse. But then there's no detection out here. Sensitivity of the VLBA just is too, by itself, is too low to see anything. On the other hand, the GBT to VLBA baselines are a factor of a few more sensitive. And so we do manage to detect the source out here. Those are the red boxes that you saw on the previous plot. But we didn't detect it, for example, on the Green Bank to Mauna Kea baseline. So the visibility should be like a part in 10 to the 8th here. Nevertheless, we see it at about 1%. These are some detections. And in fact, what these are, they're exactly the same as all the plots of the pulsars correlation functions I've been showing you. What we would expect to see for a pulsar, for a scattered pulsar, would be a spike here, and maybe, well, on a long baseline. On a short baseline, we'd see a spike. On a slightly longer baseline, we'd see some scruff down here. On a very long baseline, we'd see sort of a mound of scruff. And what we see is just a single spike. And I think that it's the finite size of the source that's producing that. So we were able to use these measurements. We find about 5 independent samples. The flux densities probably less than 10 millijansky, more like 7. Well, we can. There are 2 parameters that affect the height of that substructure, the strength of the substructure, and one is the size of the source, and the other is the index of the spectrum of density fluctuations. And so I can talk a little bit more about this. Well, from those, at least the source size and that we infer from the substructure is the same as that's inferred by deconvolution. So in other words, by subtracting off the scattering from the plot of angular broadening versus wavelength. So there's some questions. Whoops. Wow, already. Can we learn anything about intrinsic source structure from the the substructure, and can it tell us anything about scattering? And is it different from the source sizes from deconvolution? And another question is, can this sort of substructure introduce fictitious small-scale structure in sources that would be resolved without scattering? So if you looked at a scattered source that is extended, can scattering introduce small-scale structure? Well, we know some of the answers. We don't know. Well, we know that it can tell us something about intrinsic source structure, but we don't know what it can tell us. We think we can learn more about the structure, the spectrum of density fluctuations is, and we think that this will revise the deconvolution, the sizes of this black hole, whatever emission region, by about 30 to 50%. It could, and it might introduce fictitious small-scale structure in resolved sources. Let me talk a little bit about the theory. The present theory, it's all based on a calculation of the fourth moment of electric field. And we have updated it to include source size. And basically, it calculates two quantities. The mean visibility, so the average value of the visibility on a baseline, and then the RMS around that average. And I can get back to these two plots later if you'd like. So that's interesting, but it doesn't really tell you everything that's going on. So famously, all of the moments contain all of the information, but that's just one moment. If we want to understand what scattering is actually doing to the source, one thing we can do is simulate imaging the source with very high angular resolution using different assumptions about the scattering material. So this is what the unscattered source looks like. This is what it would look like if we averaged over a very, very long time, essentially over many realizations of the scattering disk. But then, depending on exactly how the scattering looks, there's a small, this scattering material can, it affects the appearance of the source in a VLBI observation in these ways. And what about source structure? Well, here's the same series of plots for a ring. And you can see that the overall ring structure is still apparent, but there's also this funny, there are differences between the two on small scales. So there's some effect of source structure on small scales. This movie might be a better description of this. So this is a very large inner scale model. And so this is a model that relies on caustics. This is very close to the picture that Yuli Penn has for scattering of pulsars by the interstellar medium. So here the scattering is done by caustics. The left picture is a source that's a small Gaussian, about that big. And this one is for a source that's a small ring, about that big. And the extent of the scattering disk is about like that in both cases. So I'm going to play a movie, and this movie runs out over a few weeks. What you can see is that not only are the sources very different, depending on source structure, but also the variation of those sources depends a lot on what the source structure is doing. So you can imagine that the RMS, some RMS measure of this structure could be equated in the two, and nevertheless a lot of information would be left behind. So I guess our goal now is to try and figure out just how to extract as much information about that source in particular as possible from the scattering. So here's some bullet points. Radioastron is producing some results. At least some of the active galactic nuclei shine at brightness temperatures of more than 10 to the 14. It's probably, I don't know. My money is on coherent emission, but I don't have much money on it. Giant pulses decorrelate over a few Earth radii, and scatterings within the nebula, it might be within the pulsar. Structure of these images of pulsars has a lot of noise-like statistics. There's some evidence for departure and Finally, there's this substructure in the scattered image of Sagittarius star. And that tells us something, and we're not sure quite what, about what is going on with the scattering and with the source. So that is the end. Thank you.
So you said the autocorrelation disappears after a few Earth radius in vision space. But how about pulse-to-pulse correlation? If it's the same scattering screen and you send antenna, you can also should be able to correlate one pulse with another. And what is the time scale of receptor correlates?
Well, the okay. As far, well, for the Crab, of course, things are hard since giant pulses don't come along very often. But for other pulsars like O329 and Vela, the results are consistent with the impulse response function being the same over spans of many pulses, up to about this time scale of an Earth, this SIS, the lateral scale. Yes, but then there is certainly the structure that we see for Sagittarius star, as well as this substructure for that Narayan and Goodman predict, only vanishes over a time scale of weeks. So it seems there's a hierarchy of if, and I don't know if it vanishes at all ultimately. So there's certainly a hierarchy of scales here involved, and so what we need is statistical measures that will allow us to distinguish what is going on all these different scales.
Do you also have space VLBI data on Sagittarius space?
Okay, well, that's a great question. The answer is we went through the calculations, and it looked like this 10-meter antenna wasn't quite big enough. But also, space VLBI antennas don't come along very often, so we thought it was worth a try, and we scheduled the telescope with the largest ground telescopes imaginable. And unfortunately, the spacecraft had this was scheduled for Monday, and the spacecraft had a glitch over the weekend, and the observations were postponed. So we're hoping that the spacecraft will recover, which it has in the past, but we don't know. So yeah, of course, since I'm addressing the next generation here, in principle, if we could solve the problem of unraveling the structure from the scattering, separating them out, then baselines that went out to a few Earth radii could map the intrinsic source at resolution of a Schwarzschild radius or less. So if there's structure there, that mission would be able to do it. So please build some more VLBI spacecraft, send them into orbit.
Are the precautionary tales of the Event Horizon Telescope?
Well, in fact, Michael Johnson is putting a tremendous amount of effort onto that. And one area of concern is that indeed the scattering can introduce small-scale structure into those observations, even at sub-millimeter wavelengths. And so we're trying to assess that, and of course that justifies further studies at centimeter wavelengths and trying to understand that as well as a theoretical wave. And he's also looked, so in fact, the first series of plots was for the Event Horizon Telescope. He's carefully trying to see what's going on with the, so I suppose the answer is he is working very hard to determine that.
Well, thank you.
Oh, thank you.